This week, we start our study of a new method for solving differential equations called Laplace transforms. This is a large topic, so we'll spend several weeks on it. This week, we're going to focus on the introduction to the Laplace transform itself, and we'll see how it applies to differential equations specifically in the following weeks. If we consider where we are in the course at this point, you can think of the types of differential equations that we've seen. We've seen first-order differential equations, and these have been homogeneous and non-homogeneous. That said, there were two kinds of differential equations that we could solve. One was first-order linear, and we also had separable. And those are two subsets of general first-order equations. There are other equations out there that we might not be able to solve, even though they're still first-order. We also notice that there's a bit of overlap potentially between those. We have also seen nth-order linear with constant coefficients. And for that, we've seen two types. We've seen the homogeneous, and we've seen the non-homogeneous now. And so that's a set. However, there's a little asterisk we're going to add to the non-homogeneous. Here we've only seen cases where the right-hand side had a nice differential family. And that limited our approach to the method of undetermined coefficients. And of course, this is the set of all differential equations out here. So out of all these differential equations, we've seen solution techniques for an important subset, but still a subset of everything that we've seen here. What we're going to try to accomplish with Laplace transforms is to focus on this region here, and what we're going to be able to do by the end is remove the constant coefficient restriction. We're going to be able to broaden that a little bit, and we're also going to be able to handle right-hand sides with a slightly more rich form by including piecewise functions, which occur quite frequently in applications. Going back to the idea of the Laplace transform, what do we mean when we talk about a transform, and specifically in this case here, an integral transform? At its simplest, a transform takes one function. So here we have the transform of, it would be a function of time as our default independent variable here. So we have the transform of a function of time. And where does that function turn up? Well, it turns up inside a definition form where we have an integral and we have a function in here called the kernel. And this kernel has two variables in it. It has t and s in it. And if you think of what happens when you perform an integral with respect to t, when we do this transformation, we are going to get a function of s, and this is often labeled capital F of s. We start with little f, in the time domain is what it's called, and we get a capital F of s back. So again, by this integration with respect to t, when we have another variable that's unspecified here, s, it's not affected by the integral, it's treated as a constant, and so it's going to be present in the final integral, whereas the t is going to disappear because this is a definite integral where we sub in the limits. We'll see how this works through examples, but it's important to note some of the archetypal transforms of this type. The Laplace transform, obviously, is high on our list for this class, and it's the integral from 0 to infinity with an e to the minus st times f of t dt. And so this would be our kernel, which has an s and a t in it. Perhaps even more popular is the Fourier transform. The Fourier transform is an integral from negative infinity to infinity, and depending on whether you're a physicist or a mathematician, the transform is sometimes written as f of t e to the minus 2 pi I st dt. And again, we have the same k of st form here, the same kind of idea of a kernel. Notice the limits of integration are different. In the Fourier transform, the limits are from negative infinity to infinity. In Laplace, it's 0. But otherwise, these are very, very similar. And in fact, if we look at the difference, there's basically a coefficient difference in the exponent. And that plays a role when we start to interpret some of the meanings of the transformed functions. Some other transforms that are important as well in the discrete time are discrete Fourier transforms and the Z transform. And what all of these have in common, again, is that they have some function, usually of time, that gets transformed through some process to give you a new function with a different variable, and this new variable has some meaning. In particular, this function here is often related to frequency. So we've seen already in the course how important frequency is in terms of looking at resonance, near resonance, things like that. These transforms, as it turns out, will let us study functions from a frequency perspective or in the frequency domain. That's a little bit further than we should get right now, though. So let's go back to practical matters. How are we going to use Laplace transforms in a differential equation course? Well, what we're going to use it for is to solve DEs. No kidding, that's a differential equation course, but we're going to use it to specifically enlarge our solution set. So what we're going to be able to do with Laplace transforms that we couldn't do before, or at least not easily, is solve differential equations with piecewise functions and with non-constant coefficients. So those will be two reasons why we're interested in using Laplace. What specific benefits are there to using Laplace transforms? Again, it's just an enlarged pool of DEs that we can solve. And we also might get additional insight into general patterns. Of the solutions. That'll come a little later. For now, we're going to focus on the mechanics. But there's going to be something in the transform version that we can look at and immediately be able to predict the behavior of systems simply by looking at the transform version. For now, though, let's move on to calculations of the Laplace transform.